Right, good afternoon, everybody. Welcome to our second iStructE Tech Talk for the South African chapter. We're carrying on with the failure analysis versus the design process series that has been run by Prof. Alex Alvin and Amanuel Gebremeskel. I'm very pleased to introduce Amanuel today. He's from the South African Institute of Steel Construction. He originally did his studies and applied his trade in America, if I'm right. So he comes with his PE and SE certification. He's been involved in the design of numerous sort of steel structures. I think is his focus really in residential, commercial, and industrial spaces around the world. He specializes in looking at the robustness of structures, particularly in the sort of accidental load cases like seismic, fire, and blast load cases. And within that, then there's fair scope for looking at structural failures and collapse. He assists clients regularly with addressing and investigating structural failures, both technically and legally, because that can be quite a hot potato to deal with. He's currently the technical director at the Southern African Institute of Steel Construction, as I mentioned. And through that, he also does a lot of lecturing, teaching, development of standards, and authoring of structural engineering books. So with that, I'm going to hand over to Amanuel. Thanks very much. And let's get on with the next part of our structural failures and collapse talk. Thank you.
Cool. Thanks, Chris, for that kind introduction. I don't know if I should have my camera on or off. Let's just save on bandwidth. Welcome, everyone. Let me just go here. That should save a whole lot of bandwidth there. Pictures are not very big, but I hope all of you can hear me. So this is a continuation of the lectures or the talk that Prof. Alex Alvin started. I think it was a month ago already, and just the end of last year. We're dealing with structural failures, and I think he did an excellent job of articulating what we're discussing here, especially he gave somewhat of a theoretical basis of the topic of failure, attempted to differentiate it, try to identify the difference between failure and collapse, which is a big deal, and talked a little bit about maybe the roles that different professions play when it comes to structural failures and collapse. So I am, as Chris just mentioned, my history is essentially that of an engineer involved in design, standards development, and let's say for the past decade or so, I've also been lecturing at the universities, primarily at WITS and Stellenbosch. So I want to sort of expose you to what I have been dealing with. And this regards both the design side and also in terms of standards development, because all of these things tie together into what we're discussing here. Now, I assume this talk is about 45 minutes or so. If Chris, correct me if I'm wrong. So I'm not going to try to take a long time to say what I have to say, but there are some key aspects of my talk that I will try to emphasize, just because I think they're quite important when discussing these failures and collapses. And I'm going to be showing quite a number of examples of stuff that we've dealt with, so that you can get sort of a preview of what people in this arena sort of deal with and how to link it back to your own practice. I assume everyone here is a structural engineer. That may or may not be true, but that's how I'm going to be talking, assuming that there's predominantly structural engineers here. In fact, maybe just a show of hands. Who is not a structural engineer here? I don't even know how to see my show of hands. Maybe Mariette will tell me.
It should just pop up. if
okay.
Yeah.
Sure. So any votes, anyone who's not a structural engineer here? Are there like people who, I don't know, lawyers or attorneys or something?
It doesn't look like it, so we're
There's
safe.
One,
then.
Amukeleni. All right. So are you an engineer?
There.
Yes.
Yes, I'm a civil engineer by profession, not a structural engineer.
Ah, cool. All right. So we have, I think the whole group is essentially engineers, which is excellent. All right, you can lower your hand. So we can get going here. And where I'm going to start maybe is go back a slide. If I can here, let me just try. Yeah, this is actually this is a slide showing the conclusions of the previous talks. If you attended them, this is actually Alex's talk, where he talked about what does failure mean, and can engineers actually be able to tell whether there's a failure or not. And then he tried to link that to this process of rational design, right? And the question is, what is rational design? So unfortunately, the way the term is used, it sounds like rational design means some sort of scientific application of your, let's call it mechanics and physics and math and whatever, to try to predict the behavior of structures and their loading, and coming up with some sort of design where you actually mitigate against failure or collapse, right? That's how it sounds, because it's rational, right? That essentially, that's sort of an enlightenment term related to science and development of science. Now, in fact, the way we design has a basis in science, for sure, which is why we spend years and years and years studying physics and mechanics and all that. But unlike how it may sound, we don't actually try to predict anything as such. That's not actually how we design. And I'm going to get into that a little bit and discuss the design process and what we actually do, as opposed to what maybe we think we're doing. And of course, the more software and analysis tools that are available, the more it looks and appears to us that we're actually doing some sort of scientific prediction of behavior and all that kind of stuff. And we're actually not. Now, we are still founded very strongly in principles of physics and all that. And maybe I'll mention a little bit about that, even though that's not what this is about, this discussion is about. The other thing that he has is at the bottom there, not at the bottom, but second sort of last, is cause, right? There's that term cause. And what he did is he differentiated between cause and reason for failure. That's a very good theoretical sort of approach to discussing things. Because, and I don't know if these are his own terms or he actually picked them up in literature, but they're very useful because as structural engineers, this is very difficult maybe to buy or to absorb, but we actually don't really care about the cause of failures and collapses. What we're primarily really dealing with is the reason, and not necessarily the reason as in, well, who went and overloaded the structure as such, but rather, was it overloaded, right? So we're, in that sense, we're very technical. The question of did someone overload it is not really in our scope of work. That's more of some other forensic work that has to do with police and other lawyers and stuff who go and investigate if there was a person who caused something, right? That's not really in our scope. But what is in our scope is to say, was it overloaded, right? And if something was overloaded based on its rational design, then that is the reason, maybe, possibly, that we can just suggest to as a cause of failure. Or we can also say, was it designed properly? That's also, and if we find that it wasn't, then there's a whole process of establishing negligence and all that. That's also yet another reason for failure. When it comes to actual cause of failure, meaning how did the actual thing come down, it is almost of no relevance to our profession. And that's always surprising for people to hear, because we all assume that if we start off assuming that we are predicting the behavior of the structure and designing the structure to resist loads by doing something scientific, then of course it makes sense that we would want to know the cause of the failure, as in how did it come apart. In reality, we do neither. That's just not what in our professional, let's call it, scope of work. So then there's that last line, which is then what structural engineers, okay, if they're not trying to do forensics and failure and all that, what do structural engineers do? And that's actually what my talk is, just so that I could continue on off of what was said before. So I'm going to talk about what do structural engineers do. All right, so to start off, any idea what this picture is of before we move on? You can put it in the chat. Has anyone ever seen this picture before? It's a collapse of a building, obviously. No. All right. So I don't see any chats. This is in fact one of the World Trade Center buildings after its collapse. This is in New York. This happened in 2001. We were just discussing, that's right at the beginning of my engineering career. This was September 11th, 2001. And it so happens, just because that did happen in 2001, a lot of my professional life has had a lot to do with trying to look into, respond to, write standards on, and learn how to prevent such things going forward, right? That's just how it happened. As in, there was a major structural engineering event right at the beginning of my working life. And the same for Chris here, who's also on the call. So, so in that sense, I got a good amount of exposure to these kinds of things, just by accident in that sense. This particular building that you see here, this collapsed building, is in fact called Building 7. Building 7 was not struck by a plane. So for those of you who don't know maybe about 9/11, which I doubt, there are people who don't know about it, but in case you don't know about it, there were 2 planes that were flown into 2 large towers in New York in 2001. And somehow, let's say a few hours after the planes hit those buildings, they actually collapsed. Both buildings collapsed. And these were very large buildings, housing about 100,000 people at a time. So these are significant buildings. And but what is interesting is other buildings that were around them also collapsed. And one of the biggest buildings that collapsed around those 2 towers was this Building 7, which is not a small building. This is like tens of stories. We're talking 50 to 70 story type building that actually came down, but was not struck by a plane. So this was the one building. Of course, after these collapses, everybody wants to know what happened, right? Now the assumption has always been that terrorists hit those buildings, and somehow that was the reason for the collapse of the building, right? Now I'm going to try to use the terms, let's call it the way they have been defined already in the previous lectures, which is reason versus cause. So the reason for the failures were terrorists hit the building, then something or other happened in the building as after it got hit, and they came down. Then, of course, the government and many, obviously, politicians, investigate intelligence organizations, everyone wants to know, why did the buildings come down, right? What actually happened? So in that sense, a lot of people are very curious to know the cause of the collapse, right? So I want to say just a few words about that before moving on. So the first initial thing was there was a lot of US federal government money for people to investigate what actually happened, right? And it just so happened I was working at a place where there was an opportunity to actually get involved in this kind of work. Now, it was somewhat marginal, meaning the actual work was being done by an organization called NIST, which is in fact the main body that was put in charge of investigating the 9/11 collapses. But there was a lot of, let's call it private companies, universities, a lot of people who got involved, somehow marginally around it, right? And there was a person by the name of Dr. Ivankiv. He's like one of these fire guys. I think he works at NIST, in fact, right now. And he came up with this theory. And the theory was quite simple. He somehow saw somewhere in his analysis and in work that there was a column in this World Trade Building 7, WTC 7 is what it's called if you want to Google it. There was one column, an interior column, that if you actually removed it somehow, if you took it out, right? If you blew it up, whatever, if you somehow removed it, that the actual structure would collapse exactly as the way you'd see it on all these videos and helicopters. Remember, there is a lot of video footage of these buildings collapsing. So in that sense, there's a lot of evidence because already the media was there after the planes hit the buildings. So there's a great deal of data available about documenting the collapse of the buildings. And then there was a whole lot of work done by a whole lot of PhDs at Champaign-Urbana and all different places doing very advanced tools to actually try to simulate the collapse. And that simulated collapse that was based on his theory came very close to, let's call it, simulating the actual collapse that you see on videos of the World Trade Building 7. So in that sense, he was actually trying to investigate the cause of the collapse, right? Now, of course, if someone can actually pin down the cause of a collapse, that's very useful information in general. It's just that we are not actually that interested in that information as structural engineers, and I'm going to explain why. Once this building came down and these theories came up, we actually went to present the results to Vancouver, which is in Canada, on the West Coast. And after this, it's like an I-Struct-E, but let's call it for North America. And this was presented, and then in the evening we went out to drink whatever at the bars, and a bunch of people came over and tried to ask us questions about the report and whatever. And as we responded to the report, what was striking was that they actually thought there was a conspiracy, right? And I'm sure by now you can appreciate that there's a lot of theories about stuff. So they actually thought we were part of some federal conspiracy and were hiding information, that these buildings were actually brought down by the government and this and that. So there was almost a fight and whatever. This was actually very, in a way, very aggressive, right? So people are very emotional about the collapse of these buildings and have very strong views on them. And what we were trying to explain to them, of course, was that, well, we don't really actually, as engineers, know if somebody attacked it or somebody actually detonated it or demolished it, and we don't care. And that was very difficult to communicate, very difficult, because people just say, well, your job is to figure out why these things came down, right? And we say, yes, we know, we have an idea, sort of, the reason why these things came down, but the actual cause we don't know, right? And even that, once you say, you can have this kind of collapse from removing a column. Of course, the next question is, well, which guy took out that column, right? Is it the CIA? Is it the KGB? Is it who is it, right? So, and we say we don't know, and that's not our job to figure that out. So that was sort of like an interesting anecdotal story. What actually got published by NIST, if you go back and now read all the reports which got published, I think the final reports got published not very long ago, maybe 2016 or something, was essentially the standard narrative, right? Which is that these buildings actually somehow had a lot of fire in them for whatever reason, and that fire somehow affected, obviously, the stiffness of the steel and other floor systems that were put in there. And of course, as those were compromised, then they compromised the column stability. And once the column stabilities were compromised, then obviously the buildings don't have a vertical system and they come down, right? That's the standard narrative, and that's what you'll find in the report. You're not going to find Dr. Ivankiv's theories and all what I just described to you. So, what's the relevance of all of this? Well, the information that is in the NIST document, whether it is actually describes the actual collapse mechanism of the building or not, is what we're interested in. And the reason why we're interested in it is because it actually helps those of us, for example, who are involved in standards development, to actually have a way to go forward to modify the standards to deal with a new type of threat that was not a threat before, right? Which may very well be a lot of fire in a building, right? We're not talking about planes hitting a building here. We're talking about the fire, because that's what NIST is focused on, is the fire. So, and in fact, that is exactly what has happened. There's a lot of work has gone into modifying the building standards to deal with fire. So let's say the fire rating of buildings that are iconic has gone up. The adhesion of fire protection on steel has become a much more onerous requirement on those who produce, let's say, spray applied fireproofing or other types of fireproofing methods. And we've had to deal with this concept of what we call disproportionate collapse, or you may have heard progressive collapse, or in South Africa, we actually call it structural integrity and robustness, which we have in SANS 10160. So all of those things were introduced into these codes all over the world as an outcome of a lot of work that came out of this. Now, this is not a lecture or a course on structural robustness, structural integrity and robustness, but I'll try to allude to it, because this is what we as structural engineers do, is design to codes and standards. I'll just give you another example. So this bridge collapse here, in fact, happened right across the street from where I went to varsity, where I studied engineering. And it also happens to be right across the street from the offices of some very big names in stability and stuff, in structural steel stability. You may know of Ted Galambos, who's considered the sort of father of LRFD and all these things. And so this actually happened right across his office, right? This is a major highway. This happened in 2007 in August. This would be like the M1 in Joburg, right? Coming down. Again, here's a collapse. And we say, well, what is the reason for this collapse, right? So we have to go looking for reasons. If you ask, what is the cause of the collapse? It is very difficult to know. Very difficult to know. It's interesting to study. Some owners are very keen to know because they would like to take that and move it on to investigate other things. But when it comes to our engineering world and the way building regulations are written, the way codes are written, the way litigation works to allocate responsibility, the cause of the collapse is actually not of interest. What is of interest here is the reason for collapse, right? So what do we look at here? Well, in this particular case, we actually find that there were a whole bunch of gusset plates, which is what you see here, that were actually significantly under-designed. What that means is that the gussets were not actually designed to be able to carry the standard loads that would have been expected on this bridge at the time that it was designed, right? And this bridge collapsed 40 years after it was constructed, 40. So again, this goes right back to the original lectures. There's no way to actually just look at something and say it works, even after it's been standing for 40 years. So this is yet another example illustrating that point. So at this point, once you've discovered this level of design inadequacy, it is actually sufficient, both from a technical point of view, from a code development point of view, and from a legal litigation point of view, to actually conclude the study. To go and try to figure out how this bridge actually collapsed, meaning the cause of the collapse, is neither necessary at this stage, nor something that is going to be of use to us as engineers. And I'm going to get a bit more into this now. So in our particular case, we designed to codes and standards. That is what we call rational design. So in a way, it's a misnomer. What we're actually saying is, yes, we know how to apply what is in codes and standards. So there is a way in which you design a gusset plate that has been established, written about. So a code and standard might say, here's a way in which you check the buckling of a gusset plate, right? Or some plate in general. You have to be able to know how to apply that, right? That equation that you find in that code and standard is not necessarily some sort of scientific prediction of something, right? It's simply a result of some study and experiments and tests that have been done for many, many, many years, and a calibration of a capacity of plates in general. Now you have to know how to apply it to this problem. So what we study in engineering is how to apply the codes and standards and their implicit, tacit or implicit requirements and interpret the results that we're getting. Now, the basis on which we actually design, since we're talking about design right now, is in fact based on this concept called lower bound theorem, which is sort of one of the theorems of the theory of plasticity. So in that sense, there is a scientific basis here, but it's not a method of predicting anything. What it is it's a method of finding a way to make sure that a building actually performs, or a structure actually performs. What does that mean? That means a building has sufficient ductility so that it can actually redistribute forces. A building satisfies basic rules of equilibrium, and that you don't have any sudden failure modes that don't give warning before you have failure. Once you satisfy these three requirements, you don't actually have to predict anything. And in fact, that is the entirety of what we do in our structural engineering work. We don't predict anything. We just design to the lower bound theorem. And you may or may not know this explicitly, but that's actually how we design. And that's why the codes and standards are sufficient and acceptable for rational design, because we have essentially a building that is designed for loads that we don't very well understand, for a structure that makes use of materials we don't really comprehend, and for behavior that we don't really need to predict, as long as we satisfy ductility, equilibrium, and we avoid sudden failure modes. And that's the whole gamut of how every standard is written, is to make sure that if you follow it, you satisfy these 3 rules. So where does software and all this other stuff come in? Because you have to satisfy equilibrium, you're going to use, of course, linear elastic theories, Euler-Bernoulli methods, Timoshenko, whatever. All these theories that you learn in physics is simply because you have to satisfy equilibrium. It's not because you're predicting anything. And that's where the confusion comes in. All right. So now that I've said enough that about design, what do structural engineers do other than design? Well, sometimes they're also asked to actually review or look and study an existing structure to say whether or not the existing structure is fine or it's not fine. That's the second type of work that engineers do, right? So when we actually get sent out to do studies of buildings, one of the more interesting kind of cases that you might come upon is you find something like this in the picture, right? So this example, in fact, is in South Africa. And the story is essentially where we got called out to a pretty large structure, sort of a gymnasium, let's call it, at a very large university around Joburg. And we saw exactly this type of failure. And this failure you could see literally at every joint in a truss, in a big truss. You know, this is one of these long trusses. It might be maybe 50 meters, 40 meters long, maybe more, across a gymnasium, right? Or a basketball court or something. It's an indoor sports facility. And when we saw this, of course, we said, oh, there's a problem. Now, of course, nothing had collapsed. The roof was still up. But if you really took your camera and zoomed in, which is what I took this picture with a appraiser. If you don't zoom in, you can't actually even see this very well because it's so far away, right? These are very high roof systems. So when you see this, you come into a structure. You've been asked to help out somehow, right? In our case, we were actually called in by the engineer who designed it initially. And when you see this, well, what's the next step, right? So you think there might be failure here, just from how this looks. There's no collapse, right? So before I showed you some pictures of collapses, right? And tried to differentiate the reason for that collapse versus the possible cause of that collapse, and that we're not really interested in the latter. But here you have a possible failure, no collapse, and someone is asking you to make some sort of judgment call, right? To say something about this building. Now, this is a very interesting area, and why I raise this is the sort of the second part of my talk, is to raise more of the area of ethics, right? So clearly you have to be a competent designer. Now you also have to be somewhat of an ethical engineer, right? And the first thing that comes up here is, well, who do you have to answer to? Who is actually the person that is the audience of your report, let's say? So if you had to answer to someone, meaning as a structural engineer, if I asked you, who do you answer to? What would your answer be? Just write it in your in the text, in the chat. I just want to see what people say. Like, you write it in one word. Who is it that you're answering to? In your understanding of what you do for a living, who are you answering to? And I'll keep talking while you put that in the chat. So we saw this and we said, oh, wow, there's a problem here. We need to try to clear this building. There were probably about 100 people in that building at the time. And we said, wow, we need to clear the people. You know, we don't want anyone here while we're doing our work. And we couldn't clear the building. People came back and said, no, we're busy. And then there were these funny looking people wearing their shades, you know, like sunglasses and stuff with American accents, talking to us. And something was just off, right? And we say, and they tell us, how safe is it to put guys up there, you know, like up on the roof? And we say, boy, we're actually planning to evacuate the building. And you're talking about putting people up on the roof. And they say it's very important. People have to get up on the roof. And we say, what's going on here? What's going on here? And there was a lot of reluctance to tell us at the beginning. And then they say, look, there's a major event that's going to happen here in 2 days. This was a Thursday. And they said, there's a major event here on Sunday. And these are VIPs who are going to be doing a talk here. And we need security. So some of our security guys have to get up on the roof. So, you know, it took another yet half hour, an hour, whatever. We were there very late. And eventually we discover that they were planning a major event in this building that Sunday where the US president at the time, it was Obama, was going to come and speak there, right? So we thought, oops, well, if Obama is going to be here, so will Zuma, so will all the elites of South Africa. So if we cock this up, this is going to be very bad news for us. Essentially, not only the end of our careers, but possibly jail time and whatever else politicians do to people that they don't like. We say, wow, we say you can't do it. You can't do it. You can't do any event here, leave alone an event with VIPs. And these were the Secret Service, obviously, with their shades who were speaking. So they obviously didn't like us right from the get-go, because we were the wrong, let's call it, we were the wrong group, right? So then eventually we say to the engineer, look, this is too hot. So why don't you tell this is a university, so why don't you tell the vice chancellor that this building has to be evacuated? So this goes all the way up to the top of the university. Now they're in chaos. So there's a major problem. And we say, can't you move the event, take it somewhere else? No, we can't do that. Okay. So then eventually, this is sort of beyond them also. This moves up and up and up the hierarchy, right? Into government and people who are security for the South African government and all this kind of stuff. Now it's very interesting. So I was looking through your answers here, and there are the first few guys, like Chris and a few other guys, say the public. Someone else, Grant, says God. Cool. EXA, users, owner, client, very cool. So God, that's very important, especially if you, depending on your, let's call it, predisposition with religion. This is for your own soul. So I would never dispute that. But here on earth, your first call is to the public. So that's public safety. And the entity that is seen, it's interesting that no one actually wrote that as their answer. The entity that presumably represents public interest is actually the state. So the way you actually have a responsibility to the public is through the state. So your primary client is in fact the state. So this is very unique for structural engineers, where that's your primary objective, is to satisfy the state. And then comes the clients and the owners and other people. So so the ethics of your profession, in that sense, is in a way very unique, because it's very rare in other professions where you might have the state having such a dominant role as being the first call of, let's call it the first client, let's call it the primal client. So in this particular case, in our case, we decided to actually condemn the building, and wrote a whole bunch of letters saying so and all that. And this was promptly ignored. So what do you do next? I actually saw one called EXA. There was an answer called EXA, which is actually very good. EXA is part of the state. It is the way in which the state enforces its, let's call it, power upon the professional, the structural engineer. So this can create a huge dilemma. I don't want to go into the rest of the story of what happened next, because it's more and more controversy. But this is an interesting case of an ethical dilemma when you face a client who might be very powerful, right? So in this particular case, we're talking about politicians who I would see as distinct from the state in this sense. So there was yet another interesting case that we had to deal with. This is now, you might guess very easily where this is. This is actually one of the power plants in not far from here in Ekurhuleni, Medupi Power Station. And here again, we got essentially hired to look into a failure of a connection in these trusses that pick up the cooling systems. So these things, they don't have water towers. These are new high-tech systems that use air cooling systems. And again, very similar story here, right? So there's a sort of a failure in a connection. And the person who designed it was out of Europe. I think it was out of Belgium. I can't remember now. And they came all the way out here to defend their design, right? And we were in that meeting. I think there was a bunch of owners and clients and this and that and Eskom and their clients and whatever. And why I'm bringing up this example here is to discuss maybe what might be unethical. And in this particular case, it is an engineer who comes and spends a lot of time and money, of literally of everyone, to try to explain their design and to justify it when the actual connection that has been put together has already failed, right? So that, not only is that a waste of time, really, but it's also just somehow, to me, professionally unethical, right? So of course, this is a very personal view, but I'm highlighting these issues as a way to bring up ethics, professional ethics. So we looked at competence and design. The second topic is there's a huge amount of ethical, let's call it burden, on our profession. And maybe we don't get paid enough to think about these things, but it's there nonetheless. And these examples, I hope, sort of highlight that topic. The third area that I want to look at is obviously the other thing that structural engineers do every day, which has to do with somehow getting involved in construction, right? So we're not looking at, let's say, you design something, you put together a construction drawing document, and it goes out, goes for bid, and then you sort of forget the project, right? Which happens a lot. You can get involved in construction. Of course, the easiest way to get into construction is if you're the engineer who works for the contract, right? That's the most clear way in which you can be involved in construction. But you can also get involved in construction, for example, if you work on a renovation project. The very nature of renovation is such that you have to get really, really involved in the nuances and the details of construction, right? Another time that you might get involved, obviously, is if you have to set or put together a specification for quality, right? Which engineers have to do in any case, at least in South Africa. Meaning, what kind of quality requirement do you ask for from the contractor in your specification? So that sort of gets a lot of design engineers into that realm, right? You have to think about the construction to a large degree. So here I show you an angle. Sorry that my examples are all sort of steel related. I'm not trying to say only steel structures collapse. It's just because that's my area of work in general. A lot of concrete buildings do collapse all the time. We just had one major collapse in Florida. I'm sure you've followed. And we have concrete buildings collapse, I would say, pretty routinely now during construction in South Africa. I'm thinking of that project in Durban now, and a few other ones, quite large ones. So you have to excuse my examples in that sense. Now, in this particular case, what I'm showing you is an angle. As you can see, there's something wrong with this angle, right? I don't know if you can see clearly, but there's some sort of crack or delamination or whatever you want to call it that goes right through the thickness of this angle, right? Now, this is an interesting problem. You as the engineer will specify an angle. When you specify an angle, well, what kind of angle do you specify, right? Well, you specify 100 by 100 by whatever S355 JR steel angle, right? That's what you write in your drawing. Do you put anything else in there? Typically not, right? So when this kind of angle shows up at a fabrication shop, and let's say gets put up into a roof, by the way, these are also real, as in like these are real, these are happening in real life currently. Then who's responsible, right? So I just want you to write in your chats, who's responsible for this, right? Are you responsible as the structural engineer, or is it someone else? Because you've actually specified what angle you need, and that's the end of it, right? So try to write in your chat in very short words, who's responsible, which part? And of course, I'm assuming you know all the parties involved in such delivery of projects. So you can guess if you don't know, it's fine. But clearly, someone is responsible here, right? Clearly. And this will affect your design. And this will affect the construction, and this will affect the structural integrity of the building. Now, why does this affect the structural integrity of the building? Very simple. Because you've introduced some sort of, let's call it defect in the member itself, which might lead to some sort of brittle failure mode. So the number one sin here is that you have a brittle failure mode. So this particular problem is worse than if you had undersized your angle. Same as that gusset plate in the bridge. That gusset plate was too thin, so the buckling mode that we expect is buckling. The failure mode is buckling. Same thing here. It's possible that we expect some sort of brittle failure mode. It may or may not be, but we would expect something of that type when there's a crack in a member. So that's the number one primal fault here, is that we've broken a basic assumption in the lower bound theorem. If you had undersized the member, that's a different problem, and you had a yield problem, right? Because you might say, well, there's going to be some redistribution of forces, and maybe I can sleep easier. That's a lesser of a problem. So that's also just about being a good designer. All right. So in this particular case, a lot of people say manufacturer, right? I think by that, what they mean is the fabricator. Then engineer and the manufacturer, someone else says. Supplier, manufacturer, buyer, installer, not the engineer. Very clever guy. Is there a difference between responsible and accountable in this case? Very cool. Contractor, fabricator, supplier, fabricator. So there's a lot on the fabricator. Everyone will get a bit. This is someone who's been to court before. Oh, it's Chris again. Manufacturer should be responsible. Engineer works off of the resistance loading. All right, cool. So this is a very interesting problem because it's a current problem. So I don't want to say too much about it, but this is something for you to think about in terms of who is actually responsible. Now, someone brought a very interesting question, the difference between responsible and accountable. That's a very interesting distinction. Now, when it comes to South African building regulation, it does say that the engineer is in charge and responsible for making sure that the thing will get built in the way, in a standard way in South Africa, which is safe and satisfies the public requirement for safety. Of course, that includes using material that is actually adequate for the stuff. Now, you as the engineer, you say, oh, how will I ever be able to figure out if the material that's being supplied is good or not? Believe it or not, that responsibility to make that judgment is actually still sits with the engineer. So if you're designing a concrete building, just to bring concrete into this mix, and you're designing it in an environment, let's say not South Africa, so we don't blame anyone here, right? Where the rebar that's supplied doesn't have sufficient ductility, and your specification does not say that someone must go and check the ductility of the steel that's going to be used. That is actually, believe it or not, a fault in the engineering document, in the specification, because you actually have some information that there may or may not be sufficiently ductile rebar. Now, in South Africa, we've gotten used to having good quality materials available for a long time. Over the past, let's say, decade or so, we've started to learn that a great deal of the material that's supplied into the country, both by local mills and by outsiders, may have diversity to it, obviously, both in quality and in every other sense. That knowledge is sufficient for you to actually now do more due diligence in your engineering design and specification. So from a point of view of the legal point of view, that's actually how it would be seen, is whether or not, so that's how negligence is determined. Now, who is accountable is based on the question of negligence. That's how the courts look at it. And what they will say is that there was no negligence, there was negligence, there was gross negligence. So they have different terms. And how they determine that is whether or not you would have done what a competent average engineer would have done in this country. So of course, one way to avoid responsibility is to have the average be very low quality, right? So, and maybe we're doing that intentionally as an engineering group, but I doubt it. So in this particular case, I've shown you this problem now. So going forward, you actually have to now think about what you might need to do when you're ordering material or you're specifying material that is to be ordered, because you are the only person who would know what the implication of such a failure in a material is and whether or not this failure is acceptable. So in that sense, there's definitely some sort of culpability by the engineer. Then obviously there's also culpability by the people who produce the steel, by the merchants, which is interesting that nobody said the steel mill and no one said the merchant in an interesting way. I think Chris said the whole supply chain, which might cover them. Then obviously there's the fabricator, and then the people who are hired to do quality control. Because you as the engineer, for example, sometimes, in many cases, have to say, something in your spec about quality control. It's actually expected. For example, in your steel spec, there stands 2001 CS1, which is typically part of your contract, which discusses how fabrication should be done. And then there's a document called SANS 1921, which deals with responsibilities and who does what. And for example, if you write AWS D11, which is our welding specification, then you're also somewhat expected to say if there is in fact a quality control measure that needs to be put in place. So all of this actually falls in the engineering realm. So again, it bounces back to engineering competence in a way during design. Last example I want to show you happened to us again on a different project. This is something actually from several years back already. We have this system that some of you may already be familiar with, that we always work with, called the fluted floor system. So someone ordered it in Cape Town, and they wanted a slab installed inside this, let's call it big hall. This was in response to COVID. They wanted to essentially double their classroom sizes. So they wanted to put a slab in this building at sort of at the height where you see these anchor systems. I don't know if you can see them far away, or sort of in the middle of the page here. And what the engineer had done, obviously, is they'd actually put in anchor systems, design anchor systems that the contractor went in and installed, and they put a shelf angle along that wall to pick up the slab, right? So you can see a slab is about to go in here in the middle of the height of this building. Now, in this particular case, this is a renovation, obviously. So clearly, you can see now that there's risk involved. I always say that renovation projects are significantly more difficult than greenfield design projects. And the reason for that being that you are actually now involved in construction, inevitably, irrespective of your scope of work. So in this particular case, we got to site and we looked around. We saw a nice angle shelf put in there on both sides of the building, obviously. This is a one-way slab system. I'll show you what it looks like. And we thought, excellent. So the slab system is here. It's going to go in. This is going to be done in a few days. I don't know. We were thinking maybe 3 or 4 days to put in the whole thing. And the span between this wall and the other wall is in the range of, let's say, 11 meters. So we had made a claim that the system that was going to be put in would not damage anything on the ground, and would not need any propping. And as you can see, the ceiling is still in, so there's no way to access it from above. This is a very, let's call it, complicated project, right? You have 10 or 11 meter spans. You're going to put in something, a big slab that's going to weigh, I don't know, 40 or 50 tons, maybe more. And you're claiming that it's not going to be propped, right? So you can't really use precast. You can't really use a regular steel structure, which would need cranes, because the client was very serious about not having their roofs affected, and they needed to start the classes immediately. By the way, this was because of COVID that they were adding that floor. They needed to space out their students. So they were looking really for a very different solution, which is what this was. But right before we started work, we looked up, I don't know if you can see my cursor, but we looked at this opening here, this door. And we were looking at it and we saw a cavity wall there, right? Which is essentially brick walls with an air gap in between them. And so sort of that just created this, brought about this sort of wariness about the thing, right? So we asked the owner, the client, who's the principal of the school. So what kind of wall do you have on this side and on that side? We were actually planning to support the slab. And he says, well, I don't know. I'm the principal of the thing. The engineer would know, right? So we say, well, can you ask, whatever. And he says, oh, well, the engineer is not here, whatever. Mayamo, this is the person who's standing on this thing. We ask him, can you go and investigate, just get up there with a chisel or something and see what kind of wall is actually currently in place, the existing wall. So he goes and he chips. And of course, we find exactly somewhat similar, which is a brick wall. Now, in a way, you can say that this is luck. Some people might say it's just competence in being able to pick up something. Other people would just say, wow, they would just look at who was at fault here. But irrespective of all of that, this is a renovation project, and you need to be extremely awake because now you're dealing with construction. And I would say the vast majority of collapses occur during construction or renovation, right? So this is in that realm. And of course, all these anchor systems, which are like epoxy then, had been anchored into brick walls. Now, as most of you know, maybe other than the people who are not structural engineers in this audience, if you anchor something into a brick wall, well, I suppose you can hang pictures off of it just about that, right? You would most certainly not put a 40 or 50 ton slab on it. So this was essentially just luck now, right? Or I don't know what you would call it, because we're about to put that weight on top of this. We've arrived on site. This has been designed. It's already been installed. It's waiting for us. And we caught it. That's our luck, I mean, because then that's why we're still alive. But there's also other stuff involved here, which is that you have to actually have a method and procedure that can lead to safety during construction and renovations. And that's why renovations are significantly more complicated than regular projects. Now, the system that was put in looks like this. This is what's called the fluted floor system. And there's Maimo again down there. He's just been busy installing these systems. This is put in entirely without any cranes. That's what you see there, that 10 or 11 meter span. There are no props underneath. And of course, then it had to be poured with concrete. And you can see a very cool picture here where the pump actually came in through the window. This is very cool. And actually pumped the slab. Now, the solution that was developed, that's what he's actually working on here. Now, of course, the client is in panic mode, right, when we discover this, because now the whole thing is off and all the dimensions are out. The engineer is also very unhappy. So the solution that we suggested was actually cutting out, a skin in the wall and actually resting the slab on the wall, directly on the wall. And of course, the question is, how do you do that, right? So in a sense, now we became the engineers. That's what Maimo was working on here, is cutting out the outside skin. So what is fascinating about this solution was, if I remember correctly, it only added to the timeline, I think, by about 2 days. I don't remember exactly, but about that. Meaning these guys actually, yeah.
So, sorry, Emmanuel, you're going to have to start wrapping up. We're running out of time, I'm afraid.
Okay.
If you could just finish this example, it is very fascinating, but yes, unfortunately we've got 5 minutes left.
Okay.
Thanks.
So this is actually one of my last slides, this system was put in. It was essentially put into the walls, the slab essentially became the classroom, and I think the whole project was done in about a week. So obviously the principal was very happy, but not necessarily because an innovative slab had been put in, but because we had actually avoided a major event on his site. And that is essentially now regarding engineers who do construction and your quality control system and learning about construction, because structural engineers don't spend a lot of time learning about construction. So to wrap up, I addressed 3 different topics. One is the design process. That's what I started off with. How do you become a competent and good designer? The second one is ethics. And the third one is, what do you do when you're actually faced with an actual construction, right, that you have to address, either because you work for a contractor or you're doing a renovation project, all right? So sorry, Chris, we always run over. I see that Alex also ran over last time. But
no, you guys like talking, it's fine.
Yeah. So if there's any questions or comments, you guys are welcome to do it in the last 2 minutes. I'm actually done with my slides. That's what it looks like from below. That's the essentially during the pour, and I was the one who was standing underneath. So I'm very happy to be here with you guys, having avoided that catastrophe.
Thank you very much. Very interesting talk.